Testing, testing, 1, 2, 3, testing, testing. Checking for latency. Seems like the stream is cutting in and out a little bit. If this is a problem, then I might have to go bump the router to see if I can fix it, but we'll see. How's everybody doing today? Hope everybody's doing okay. It's a Tuesday, so that's about as much as you can ask for a Tuesday. Getting some weird latency. I'm just watching on my phone right now, and the stream hasn't actually kicked in yet, but maybe it's behind? Yeah, it's 2 minutes behind live. Good lord. Alright, maybe that'll be a bit better. Ho ho! Alright. Cool. Alright, so let's get started then. How is everybody today? I hope everybody's doing alright. I already said that. That's okay. So, last time we were talking, well, maybe I do have some housekeeping related announcements. We believe that Jupyter might be functional at this point in time, so you guys might be able to go check out your assignments. You might be able to fetch them off of the Jupyter server. So that will be an interesting thing for you guys to go and see if you can do that. If you can't do that, then please bother Mark Hutchison about it, not me. No, you can bother me about it. Just kidding. But yeah, so Jupyter should be up. Assignments should be up. You guys should be able to start working on them. We haven't necessarily covered the stuff that Assignment 1 is about yet because we're a bit behind on the lecture material, which is a situation exacerbated by the inordinate amounts of time I am taking to describe things. But, you know, that's kind of just how it goes sometimes. I'm gonna try reloading this on my phone to see if the chat is not just the chat didn't look like it was being updated, and I'm pretty sure you guys are pretty active in terms of chat, so you know. Yeah, there you go. There we go. What are we supposed to study post lectures? So the intention is that after the lectures you do the assignments. The best way to solidify the concepts that we're talking about them is to put them into practice. So I would recommend doing the assignments. Yeah, latency, audio delay, bluff. Okie dokie. Yeah, I was pretty sure. On music from Undertale, sure. No, it's copyright. No, I had to get stuff that was not copyright. Okay. Yeah, so the first assignment is due on the 27th. It's supposed to start at the beginning of next week, so you guys have plenty of time to fill it out. It's not particularly difficult either. I feel like, generally speaking, if you understood the stuff that we were talking about in the last class with respect to loops and branches, like not even like understand them completely, but if you have some rudimentary understanding of those things, you should do all right on the first assignment. The first assignment is mostly about expressions anyways, which is our topic 2 set of slides. So there you go. There might be some confusion between the 27th and the 28th. Let me just check my calendar. They're always due Sunday at midnight. So that would be the 27th at 11:59 p.m. because there's a little bit of confusion with respect to whether midnight is, technically speaking, the previous day or the next day. So if I said midnight on the 28th, then that would be probably construed as you'd have the entirety of Monday to do it, which is bad. Yep. Anyway, so let's get on with it. Hopefully any questions that you have about the assignments will become clear once you guys start looking at them. And also, that's kind of what the Piazza Forum is for. So, we were talking about this flowchart example for the median of 3 numbers. We'd gone through that. So, here we go. New material. Annotation of flowcharts. You can annotate flowcharts in order to tell which conditions hold true at various points in the flowchart. So, for example, at this point, x is less than y because it had to be true here for you to get down this branch. These are declarative descriptions. They help us understand the algorithms and argue about their correctness. And it is good practice to explicitly write a few of them. However, be careful about over-annotating, because it is entirely possible to just completely clutter up a flowchart with all of these annotations. Just don't be afraid of doing them. Annotation is not anything you'll ever be tested on. So, 2 quick notes about Jupyter files. How do you save a Jupyter file after finishing? First of all, you save them with Control-S in the regular manner that you would save a document. However, submitting them, you have to go back to the Assignment tab, and there is a submission box. There's like a box that allows you to submit the Jupyter files that you have. It's like fetch and submit. You have to click submit in order for the file to be submitted. If you don't do that, then you got nothing, and I will have no mercy for you if you say, "Oh, I did it, but I didn't submit it." It's like, yeah, okay, and I bet the dog ate it too. So, what is the maximum number of operations to compute the median of 3 numbers? There's a few like Q&A type slides in the remainder of this. However, we have to motor if we're going to keep on schedule. So I'm just going to go through things a little more quickly than I normally would. So, if we have this algorithm for previously, what's the maximum number of operations that we could possibly do? Well, this is an operation, so 1. This is an operation, so 2. This is an operation, so 3. And this is an operation, so that's 4. So the longest path through this algorithm is 4 deep. So the maximum number of operations required is 4. Conversely, the minimum number of operations on any path here is 3. So you might say the best case scenario number of operations required is 3, and the worst case scenario number of operations required is 4. Another question. The dog took a couple of bites. Ha-ho! Awesome. If I hit submit, can I submit again? Yes, you can. You have as many submissions as you like. I see my stream has frozen. I'm going to just see if that's actually true. Okay. Looks like it was just my phone. Okay. So, yes, you can submit the assignments multiple times. You get as many submissions as you like. However, we take the closest submission to without going over the due date. Kind of Price is Right rules. If Jupyter does not work for you, yes, you can submit through Avenue, through the Avenue drop boxes. If you have programmed before and you have lots of experience, can you do all the assignments up front? Yep, you can do them in whatever order you please, as long as the correct due dates are met at the correct time. Cool. All right. Good. I guess my phone's just a little wonker-doodle. Anyway, so here is a flowchart for determining the minimum and maximum of an arbitrarily long list of integers. So, just to go through this algorithm, the first thing we do is we initialize I, min, and max to 1, t0, and t0, given that we have as inputs a range of integers ti for I is less than or equal to, for 0 is less than or equal to I, which is less than n. This is a series of n temperature readings. We also have an integer n, which is greater than 0, i.e. the list has to have at least one element in it. So, as outputs, we get the minimum temperature in the list, min, and the maximum temperature, max. So this is how this algorithm works. We initialize I, some variable I, max and min, to 1, t0, and t0. If I is less than n, then we do the rest of the algorithm. If not, we exit. We then test to see if ti is less than the minimum. If it is, we assign ti to the minimum, so the minimum becomes ti. If not, we check to see if ti is greater than the maximum. If it is, then we set the maximum the maximum becomes ti. Otherwise, we just skip that bit, and no matter what happens up here, I is incremented by 1. And then we reevaluate the loop condition. So let's see what this would look like in terms of a... Let's see what this would look like in terms of an algorithm. Get it? temp.py. So, converting this flowchart into an algorithm. First, I, min, and max are equal to, well, you know what? Let's define this as a function. Let's say t, which this will be your first rough introduction to seeing what data structures look like in Python. But that's okay. So we take in this t, where t is a list of temperatures, t at 0 and t at 0, while I is less than n, if t at I is less than the min, min is equal to t at I. Otherwise, if t at I is greater than max, max is equal to ti. There's nothing to do on the else branch of that, so back to the level of the main loop execution, I is equal to I plus 1. Oh, I need to actually call this min-max. So now that we've written, okay, I have a couple of questions about this algorithm. Oh, can you change the background color? Well, let's see here. Text editor, preferences, editor, fonts and colors. How about this one? Maybe this one? No, that's the one I was using. Dark theme forever, so it's got to be a dark theme. There. How's that? Is that any better? Cool. So, oh, and maybe I can blow up the font a little bit while I'm at that. Doop, 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 doop. There, that should be much more readable. Hopefully that's much more readable. Ho-ho. Whoa. Get out of here with this light mode is better than dark mode nonsense. I know, well, you know what? This is programming, so there you go. It's actually very typical for programmers to program with dark themes. I don't know, it's a cultural thing, I guess. Anyway, so the question was, why am I indenting things in the manner that I am? The indentation in Python tells you where what things are inside other things. So because everything inside of here is indented to this level, all of it is inside of the loop. Everything inside of this branch of the t is less than min if statement is indented one level further. So, oh, and I need a colon there. So you can tell that this statement is inside of this if statement, this else branch of the other if statement, the while loop, and the function definition, because it's been indented 4 times. So the number of indentations is the number of things a statement is inside. Hopefully that, there you go. So, now that we have written the function, we have to actually use it. So let's say x comma y is, or you know what, we actually have to return from the function as well. Return min comma max. In Python, it's possible to return more than one thing from a function using this comma syntax. Something we'll talk about in depth a little later on. So min-max, let's have a list of temperatures randomly selected from single-digit integers by my fingers. And a number of things in that. We can technically calculate that from the data structure itself, but for the purposes of this algorithm, let's just count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 entries. There we go. Print max maximum equals x, and minimum equals y. So when you guys start becoming top programmers, you will find that the better a programmer you are, the more you use copy and paste. It just seems to be the way that things go. So let's open up another terminal session in which we may execute the following code. Python 3 temp.py. There we go. So the maximum has been determined as 1 and the minimum as 9. That seems to be the inverse of what we were looking for, doesn't it? The program does execute, though. So, let's see. Is it because I've mixed up here? Yes. Okay, yeah, see what I've done? Minimum is the first argument, which is x, but I'm just printing it as the maximum, so that's on me. What are you talking about? I never make mistakes in programming while teaching a class. Alright, so, boom! There you go. So the minimum is 1 and the maximum is 9. There you go. The other way that you could do this, if you wanted to, just so you know, is you could also just print the maximum of this thing. Because that also works in Python. So it's kind of a lot of copy-paste oriented programming. Yes, indeed. So that is how you would create an algorithm from the flowchart that we have discussed. I realize that went pretty quickly for some of you. If you're worried about, oh man, I have no idea what's going on, that was so crazy. It's like he was speaking a foreign language. It's kind of true. So there is this sort of truism about the teaching of programming, which is sort of the bane of the existence of programming teaching professionals, such as myself. But it is nevertheless very true. There's kind of this poorly defined conceptual barrier that most people have at birth with respect to how does programming work. So you have to kind of train yourself mentally to think in programming code, and until you've been able to accomplish that, programming will take you like 4 to 10 times as long as it takes someone who has had this click. So there's a clicking moment where like all of the programming ideas that you have fall into place, and suddenly you'll be able to program like nobody's business. But until you have that click moment, it's going to be a bit of a slog, and the slog should be towards achieving the clicking of the ideas. Unfortunately, what makes programming click for someone is different for every person, and it's not well defined, and the only real way to get it to happen for someone is for that person to like try programming and to keep bashing away at it until it clicks. So yeah. So I'm sorry, but that's kind of just the way it is. There are a couple of slides here about going through this program in detail, like what is the minimum number of comparisons, maximum number of comparisons. I'm going to skip these slides in the interests of getting the heck on with the course. I'll just skip to the conclusions. So the question is, what's the minimum and maximum number of comparisons? So if you're looking at this algorithm, the thing that we're trying to sort of lead towards is that this algorithm will have a different number of operations executed depending on the arrangement of the data that's going into it. So since so for example, if you take a look at this inner part of the algorithm, the shortest way through this algorithm is for ti to be the minimum number. So in order for ti to be the minimum number each time the loop is executed, you would have to have data that has been arranged in ascending order. So if you have, 2, 4, 6, 7, 8, 10, 13, that's data that's in ascending order. So you'll always be going down this branch of the if statement when you hit it, which means that the number of operations that you're performing will be minimized. The other perspective is, when is the number of operations maximized? And that is, in fact, in the opposite case. When each element is... Well, I think I reversed that again. No, it would be descending order for each new number to be the new minimum, and it would be ascending order for each new number to be the new maximum. So if it's in ascending order, we have the maximum number of operations being executed per loop iteration. If it's in descending order, then it's the minimum. Yeah, you could also just use the sort operation. So, there we go. So let's talk about programs. Programs are algorithms that can be executed automatically by a computer. Fixed program computers serve only one purpose. Some early computers, such as the Manchester Mark I, and other very simple computational devices like digital clocks and washing machines, are fixed program computers. There's no way to change the program that is inside of your washing machine. Well, technically this is less true these days than it used to be. But what we are using right now to view this lecture is a stored program computer. Believe it or not, at a certain point in history, this was a huge innovation, that a computer might be able to, rather than be hardwired to perform a particular calculation, the computer might execute instructions that might be variable, rather than only being able to do the same thing each time. Yes, and I'm sorry, the Manchester Mark I was one of the first stored program computers. So, a stored program computer achieves its universality by storing instructions in the same way as the data, allowing programs to be changed. So the idea, so basically, back in the old days, you had computers that operated. Basically, computers were just electronic circuits, and you had, in order to modify the program of the computer, you had to actually move wires around. The data, however, was stored separately. So once we came up with the innovation of being able to store the instructions to the computer in the same medium as the data was being stored, that allowed us to modify the programs of the computers, and modern computing was achieved. Incidentally, this concept of computing is very highly related to the concept of the Turing machine. Alan Turing is kind of one of these great granddaddy of computing type figures, highly prominent in the breaking of the Enigma code during the Second World War, which led to the repulsion of the Nazi invasion of England during the Second World War, which changed the course of the war. It allowed for misinformation campaigns that were able to distract the Nazis about where the particular point at which the D-Day landings were going to occur, which was a key strategic advantage that they had, that allowed them to make landfall in mainland Europe, which eventually led to the Allies getting to Germany around the same time that the Russians did anyways. But anyway, there's a movie about it. I think it's called the... I forget what the movie was called, but they did a recent movie about Turing with Benedict Cumberbatch, and it's pretty good. You should watch it if you're interested at all in the history of computation as a science. I'm no longer going to answer questions from people about, is this slide going to be on the test? I'm not going to answer those questions anymore. So, there we go. So this is the von Neumann computer architecture, which is the primary computer architecture that's used in modern computational devices that allows for the stored program computer architecture to be distributed across a large number of different types of devices. So in general, this is how a computer works. You have input things and you have output things. What is input and what is output depends on what type of computer you're talking about. In computers, in the conventional sense, what we now know to be the conventional computer, an input is something like a keyboard and a mouse, and output is something like a monitor and your speakers. In the context of a smartphone, the input would be the touch surface of the phone, the output would be the screen itself. Although a great amount of effort has been put into smart devices to try to give the illusion that the input and the output are the same thing, from an electronic perspective, they are very much not the same thing. The input is completely distinct from the output for the purposes of computation. Can you watch Imitation... Imitation Game is what it's called, yeah. Can you watch it as part of the curriculum? There will be no testing on it, but you may watch it if you like. Yeah, I would consider it I would consider it important to the understanding of how computers, the history of computation. So it's marginally related enough to be worthy of watching, I would say. I'm not going to require it, though. So, inside of the computer itself, you basically have two primary mechanisms. You have the central processing unit, or the CPU. The CPU is the thing that does the calculations, and you have the memory unit. This is the thing that stores the results of the calculations. Within the CPU, you've got the control unit. The control unit essentially makes sure that the correct pieces of memory are in the correct positions in order for the arithmetic logic unit, or the ALU, to be able to operate on them correctly. The memory management systems of modern computers are very complicated. They have random access memory, read-only memory. Random access memory is your RAM chips. It's sort of your computer's working memory. ROM, or read-only memory, that's your file system. When you're looking at your files on your computer, this is ROM memory that you're looking at. You then have other, more abstract forms of memory. Inside of the CPU itself, there are memory holding elements called registers, and you also have a thing called cache memory, which that's C-A-C-H-E, cache memory, that allows the computer to store intermediate transactions in a manner that can be accessed much more quickly. So there you go. Yeah, I believe Imitation Game's on Netflix, yeah. So this is how a computer works. Instructions are stored, loaded into the CPU, executed. The results of those calculations are put back in the memory. That computing is that plus the context, and that's all that computing is. So, CPUs operate on bits. So when you are talking about computer memory is stored as a series of zeros and ones, and you've probably heard about the binary system and binary code before this. Bits are typically grouped into bytes. Bytes are 8 bits long, and into words. The word is the operational size of the CPU. So if you have a 64-bit architecture, which most things do these days, cash money, yes. Most things have a 64-bit CPU these days, so the word size for a 64-bit CPU is 64 bits. CPUs contain their own very limited memory called registers. The main operations in the CPU are to load a piece of data from memory into a register, do arithmetic operations on some data in the register, store the data from registers back into the memory, and jump to another instruction based on the value of data in the register. So, that last one gets into the control of the program itself. So when we are asking the computer to do things like branch statements and loop statements, we are basically we're coding the computer to jump to particular statements based on conditions. And that's another sort of primary thing that the CPU will do. Your program is stored in the computer as a set of instructions, and there is one particular register in the CPU that points to the instruction currently being executed. When that command is executed, it goes to the next one, and then it goes to the next one, etc., 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 unless it's told to jump somewhere else, which is what happens when you're in a loop. So there you go. So let's talk about programming languages. There have been a number of programming languages through history. One of the earliest is called Fortran, or Formula Translation. It was originated in 1958, and it took machine language, it translated between mathematical expressions and the machine language. Prior to programming languages, everything had to be calculated in terms of machine language, which is a pain in the butt. Fortran was originally programmed on punch cards. This is a picture of a punch card right here. So this is how you used to program in the 50s. you would have a stack of punch cards. You would take a hole punch, special one that made these little rectangles, and you would manually, with your hands, punch out all of the holes on the punch card that indicated the operation that you wanted to do. You would then put that card onto the stack. You would take your next card, punch the next operation, put that onto the stack, etc., etc., etc. And if you were smart, you would label your punch cards as to the order that they were in, so that if you accidentally dropped your stack of punch cards on the way to feeding it into the slot in your computer that would actually execute your punch card operations, you drop them on the floor, you would be able to put them back in the order that they occurred in. Otherwise, you basically just have to start over. So that's a very long way of saying that modern people do not appreciate how hard things were back in the old days. Just saying. To be fair, though, much less was expected of computer programs in the ancient days. The idea of getting one of those computers from the 50s to do even the most simple, getting it to play Pac-Man would have been like, good luck. So anyway, eventually, computers started hooking up CRT cathode ray tubes to computers so that lights on a screen could be manipulated by a program. Once this happened, you could get away from punch cards and program into the actual computer itself. We're starting to get into the 60s and 70s here, and starting to talk about programming languages such as ALGOL and Pascal. Not Haskell, Pascal with a P. Interestingly enough, computers have been good enough for the existence of graphical programming languages, so programming languages where you're like manipulating blocks of code and sticking them together that you might have done when you were in elementary or high school. While these are possible, generally speaking, the dominant form of programming still done by professional programmers is textual programming. This is because it's faster, and for no other reason. You can have as nice a GUI as you want for programming, but if it isn't fast, nobody's going to use it. Yes. So let's talk about what a compiler is. Compilers are programs that make programs. A compiler translates high-level programs into machine language. In a high-level language, you might have something like U is U minus V. In machine code, you load U into R1, then you load V into R2, you subtract R1 from R2 and put the result in R1, then you store in U R1. One line in something like Python can map to many machine language instructions. And the more complicated a thing you're doing in Python, the more machine languages that, yeah. The more complicated the thing you're doing, the more machine language instructions you're generating. And the goal of high-level, high abstraction level languages is to be able to produce as large a number of machine language instructions from as few a number of language constructs as you can, because if you know what you're doing, you can program very quickly that way. So good question about the assignments. Are they graded immediately, or do you have to wait? You have to wait. We actually have to manually auto-grade all of the assignments. I'm hoping this semester that we can have the feedback from all of the assignments released back to you, the students, by Wednesday, by the Wednesday after the Sunday that they've been submitted, but we'll see. Yeah, machine language is really complicated. So, let's talk. That segues nicely into a discussion of high versus low-level programming languages. So, high-level languages include things like Python, R, and Haskell. Although I'd say Python is definitely not as high a language as Haskell. Haskell should be way up here. But anyway, these high-level languages provide the programmers with a lot of abstractions to formulate complex mathematical expressions easily. I think the only reason Python gets considered a high-level language is because it's got a well-supported set of libraries. Would it be possible for you guys to say, we haven't learned this operation yet, so you get a 0? No. No, all of the operations that we are going to ask you to use in the assignments will be things that have been covered in lecture. Yeah. Okay. You said that compilers translate code into machine language. Is that the reason C is faster than Python? Yes. So, if I can just return to the idea of compilers, I think we've got a slide on this at some point. But so C is not C is a language that is compiled. So there is a compiler. It makes object files, which are machine code. In Python, things are slightly different. We have a thing called the Python interpreter. The Python interpreter is it's a process, it's a program in and of itself that provides a layer of separation between machine code itself and the Python script. So Python is actually not even technically considered a programming language in the proper sense. It's a scripting language because it's, well, I mean, okay, I'll walk that back. With Python, it is possible to produce executable files, but most of the time when you execute Python, you're executing a script. You're not compiling a language. So it runs into, yeah, okay, yeah. Anyway, I'm getting a little bit here and there. But yeah, a low-level language is not just, it's low level, which means it's less abstract, which means there are fewer things helping you. You have more direct access to the memory and hardware, however, so if you know what you're doing, you can optimize low-level languages to a much greater degree than you can high-level languages. Have I told the Roller Coaster Tycoon story in this class yet? Somebody tell me in chat if I've told the Roller Coaster Tycoon story, and I'll do this slide. So, you also have a difference in programming languages between those that are application-specific and those that are general purpose. So, application-specific languages do like one thing very well. SQL is just for databases. HTML just does web pages. R just does statistics. General-purpose languages can be used for lots of different things. Python can be used for web pages, databases, and statistics, and a bunch of other things besides. So can things like C and Haskell. Okay, so this is the Roller Coaster Tycoon story. Way back in the ancient days of the 90s, there was a program called Roller Coaster Tycoon. It was a video game. It was considered exceptionally innovative for its time. If you've never seen Roller Coaster Tycoon, you basically make a little theme park, you design roller coasters, and then a bunch of little NPC guys walk around your park and ride your roller coasters, and they have various things about them, like their enjoyment and how much they have to go to the bathroom and whether or not they're hungry. And the thing about Roller Coaster Tycoon is that it allowed a really large number of these NPCs to occupy a park simultaneously. Far more independent AIs than had ever been seen in a video game before. You could have like up over 1,000 of them at once on a Windows 95 computer. So the way that they were able to do that is because large portion, well, maybe not large, but important parts of the code for that game were optimized in assembly code. They went right down to the lowest level programming language they could get, and they optimized in assembly, and that meant that they could push the program way beyond the limits of anything that had been accomplished prior to that. Of course, now computers are good enough that you don't have to, it's kind of a pedestrian concern at this point. You could easily have 1,000 of something running around. Although if you were to do that in Unity, 1,000 game objects in Unity all doing stuff simultaneously, if you didn't write it correctly, you would start running into optimization problems. Anyway, so there is a difference between interpreted and compiled language, as I've said. Programming in compiled languages like C and Java, the program source code is translated into machine code in advance. It's like, do you generate the program in machine code up front, or do you generate the machine code line by line as you're executing? If you're doing it as you're executing, that's an interpreted language, and that's like Python. This makes Python slightly, what am I trying to say? What? Poof. Come here, you. Ugh, the cat's bothering me again. Yeah. So, this means that syntax errors, for example, in Python are found as you're going through the program, whereas in a programming language like C, all of the syntax errors are presented for you up front. So you don't have to worry about syntax errors at runtime. So, generally speaking, oh my goodness, can I get through the next 4 slides? Lightning round, here we go. So, there are 3 main categories of programming languages. You have imperative languages, which are also called procedural. They're sequences of operations. Object-oriented languages are generalizations of the imperative paradigm. We are using imperative/procedural languages in this course. You then have declarative and functional languages. Those are 2 different types of things. Programs which focus on functions and relationships between functions. If you do CompSci1JC3, you'll do functional languages there. Yes, the cat's name is Marimba, or Rimby for short. And then you have logic languages, which focus on automated reasoning about logic statements. There are differences in programming languages, differences in syntax and notation. For example, in some cases you have bang equals for not equals. In some cases you actually have a strike through equals character. You can have begins or ends for block delimiters or curly braces or indentation. There's variance in the degree of type checking that goes on. Java is statically type checked. Python is dynamically type checked, and C is not very much type checked at all. You get varying levels of support for abstraction methods, which allow for larger programs. So classes and exceptions are things that exist in Java and Python, but not in C. You also have the availability of standard libraries, etc., and the portability to other platforms. And that's time. Unfortunately, I have to get to another class. We'll cover the last 2 slides at the beginning of the next lecture. Ta-da! Okay. We'll get into what static and dynamic mean at a later point in time. Okay. There we go. Cool. All right. Thank you very much for your time and attention, folks. We'll see each other again on Thursday.